So we'll continue with our look at volume by slicing, but now let's look at a hemisphere. So looking at this picture here, we have a hemisphere with radius 4. And again, let's use slicing. And just as before, let's continue with the idea of using horizontal slices. So if we were to envision an arbitrary slice that's horizontal, much like before, I'm going to have this very thin kind of thickness here, if we think about that. And again, I want to think about looking at the volume of one of these K slices so that we can generalize. Now, thinking about one of those pieces, I'll point out that if I were to take out that slice and kind of consider it by itself, notice that we don't get quite a perfect cylinder. So the radius of the top circle is going to be slightly smaller than the radius of the bottom circle. So you get this kind of almost cylinder. But think about every time we used rectangles when we were looking at the area under a curve. Often that wasn't exact, but we at least fit a rectangle to it. So it's the same idea that I could choose to fit a particular cylinder to this. And that's what I'm going to do. So cylinders are kind of playing the role of rectangles for us here. Now with that, that means that just like when we talked about left, right, midpoint, and so on, arguably I have a choice of which radius to choose. The largest possible radius would be the one at the base of our almost cylinder, and the smallest, the one at the top. But as we send the number of slices to infinity, it won't matter which choice we've made there. So keep that in mind as I do make some arbitrary choices along here. So now we're at the situation where we can start the process that we established in the previous video. So first of all, again, I think about delta H. So if I'm slicing this horizontally, then I can see that I'm moving upward from the base to the top. So we're looking at changes in the H value. And in order to think about delta H, we take the length of our interval of H values. So just as we've established the radius is 4 here, that also tells me the distance from the base to the top. So that's going to be 4 is the length of the H interval, and we're dividing by the number of slices n. Again, H sub k is the smallest height value, 0, plus k times delta x, so we get essentially 4k over n. And the volume of a slice is, again, the volume of the associated cylinder that we see. So for this, I'm going to write pi times rk squared delta h. And if this is my kth slice, right, I can choose my rk, for instance, to be the top r value or the bottom, wherever I'm fitting that. But there's one big difference here that I want to emphasize from when we looked at the cylinder example. So if you think about the almost cylinders we're getting here, I drew one very close to the top in blue up here. But notice that that's going to be quite a bit smaller than the associated almost cylinder you would get very close to the base. So in the cylinder example we saw, all of the K slices had the exact same volume. That's not going to be the case here. So the volume of each slice is different. And in particular, what I want to draw your eye toward is the fact that the radius rk of the kth slice depends on the height, let's call it h sub k, of the kth slice. In the example where we were looking at a cylinder in the previous video, the radius was always 2, and it didn't matter how high off the base we were. So when this happens, what we have to do is we need to find a relationship between these two variables. Okay, so that's my goal. We didn't have to do that in the previous video because the radius was always 2. And so I'll point out that once we've established that our integration variable is h, then any variables that show up that are determining the height should be in terms of h. And so right now, r sub k depends on h sub k, but the way that I've set up my volume formula doesn't make it clear what that relationship is. So how do we find that? What we want to think about is coming back to, again, how h sub k and r sub k are related to our original hemisphere. So if I go back up to my hemisphere, imagine instead of this three-dimensional view that we're just looking at the front of this, in which case you should think that we would see just a semicircle. So if my slice is up here, the variables I've been talking about, well, this would be h sub k. That would tell me how far off the ground we are. Again, I'm making this all kind of two-dimensional. I'm squishing the delta h view as well. And r sub k would represent this distance. And we need to come up with a formula that relates those two. Notice that I can now write in here, draw in here this line, and what we have is a right triangle. Now, that means we can use Pythagorean theorem to relate these two things. And what we have to keep in mind is that I know that the pink line has distance equal to the radius of the larger hemisphere, and we know that that's 4. So from Pythagorean theorem, then we know that rk squared plus hk squared is equal to 4 squared. We need to be able to replace the reference to rk in here, which is rk squared. So what I've determined from this is that rk squared is always going to equal 16 minus hk squared. So noting that, then we can say that the volume of the kth slice can be represented now as pi. We had rk squared before. I'm going to replace that with 16 minus hk squared. And this is then times the height of the almost cylinder, delta h. Now, where I'm putting in hk here, again, is that reference I was making before that I'm making a particular choice of a Riemann sum. You could put in hk minus 1. You could put in the average of hk and hk minus 1. But again, since I'm heading toward a definite integral, I'm not going to worry too much about which height value I'm choosing within my subinterval. So this is my v sub k. So then if I want to now find the volume of the entire hemisphere, here I can say the volume is approximately the sum of my n slices. And I want to pause for a moment and point out that here the approximation symbol is necessary. When we did this with the cylinder example, they are in fact equal. But if you think about what we're actually getting here, let's just even draw 2 pieces because it's not so easy to draw. If you think about having one cylinder and then we're putting on top of that, right, this next one. I mean, if we continued this, instead of having a semicircle type appearance, we'd have almost like a tiered cake. And of course, the more pieces we have, then we'll see that this will become our desired shape. But this is an approximation for finitely many pieces. And this sum is then, we've established, equal to the sum of pi times the quantity 16 minus hk squared, delta h. And if I want to compute the exact volume, I then can say, let's take the limit as we send the number of slices to infinity. And this gives us a definite integral. And we need to find that definite integral. So again, delta h becomes dh. Notice that our integrand is pi 16 minus h squared. We don't write the k, because remember the k is a reference to which slice we're on, and in this case, we're no longer considering the slices. And again, I have to be very careful about my bounds. I don't want to be distracted by the bounds on the sigma notation. Instead, we know from our original picture that h is ranging from 0 up to 4 when we're at the top of that hemisphere, because that's the radius of that. So my bounds on h are 0 and 4. We can anti-differentiate. So we get pi times 16h minus h cubed over 3. We're evaluating this from h equals 0 to 4. And this yields pi, oops, if I can write pi times 4 times 16 is 64. 4 cubed is 64. So we're left with pi times 2/3 times 64. And so this is going to give us 128 pi divided by 3. So in the next video, we're going to do one more example of this. Again, what I hope you'll notice is that the connection between these 3 different examples is the process that we set up, and that kind of breaks it down into the steps that we need to get to that end result. But again, what we'll see in the next video is encountering what I put in red up here, a situation where the volume of my slice very much depends on which slice I sit in. It's not going to be constant. So we'll have more practice in that and think about how to again, set up a relationship between the 2 variables involved.